Two-stroke ignition boxes. What do you know about ignitions on two strokes? What do they do? How do they work? And why can we and do we choose to tune them in certain instances? Let's take a deep dive into how two strokes work, specifically relating to ignition boxes, and then later on we're going to build on this video about fuel injection with two strokes and what that means. So let's get to it. How does a two-stroke work? Well, a lot of people, even engine builders, seem to miss some of the basics these days because a lot of this stuff was figured out a long time ago, and so it's been taken for granted as to what this stuff can do. So let's get to the basics on how an ignition box works on a two-stroke, what we can do with it, and what we can't do with it. By bolting on one of these to your bike, will you instantly make more power? By bolting one of these onto your bike, will it be better power? Is it more spark? Is it hotter spark? Or is it something else that these boxes can do? Let's answer that in this video. So this is what a basic two-stroke ignition curve looks like on a modern two-stroke. This could apply to almost all the brands of motorcycles out there, whether it's a Yamaha, a KTM, or formerly back in the Kawasaki days and Suzuki days. They all looked like this. Hondas as well. Now, they all varied a little bit. This could be a Honda, this could be a KTM, this could be a Yamaha. But they all had a generic basic curve. This would be very appropriate for a hopped up Hizoot 125. A 250 would look the exact same, except this would move over to work in the RPM range that the 250 runs at. So on a 250, this would condense in, and here at about 8,000, you would see this downward slope, and it'd settle, and then it'd go back in. So let's talk about this curve and what and why it's trying to accomplish certain things. And then also, what are these three lines? That could represent three different bikes. That could represent actually three different stator settings on this curve because all the curves are the same. So by advancing the stator, you would go from here to here to here, right? And then let's talk about what these can do and what the whole theory is. Let's get to it. This is an awesome video. If you want to get smarter, watch this video, hit the like button. It means a lot to me. So this would be three different flat rate ignition curves. Same chart, condensed down, 5 degrees timing, 10 degrees timing, 20 degrees of timing. That's an old school ignition system, non-digital, non-programmable, flat rate ignition. And a lot of two-strokes in the early days had this. This would be very similar to an ignition on your car that's been locked out on mechanical or vacuum advanced so that it just runs one ignition curve. Anybody in the car world will understand what I'm talking about. So let's talk about if you had just one ignition curve and you had nothing else special, what would it do to you on the dyno? So if you had one ignition curve and it was 20 degrees of advance and you had a set pipe and a set port and a set engine, everything the same, you'd get a dyno curve like this. Then you would go to 10 degrees of timing and you would get a dyno curve like this. So surely we make more horsepower because this would be about right for that engine. However, we would lose some bottom end and not be optimized because if we go to 5 degrees of timing, we're going to lose a lot of bottom end. We're not going to make more peak horsepower at all, but then we could pick up some over rev. So what would be perfect? How could we make this be even better? Well, that's what these curves do. This is what digital CDI boxes brought to the game, is you could program anything you wanted in that ignition curve. So you could start off at 20 degrees. And then when the dyno said, hey, that's not the best, we could retard progressively down to 10 degrees so that we could match the curve from here to here. Now we've filled in this horsepower curve, but if we stayed at 10 degrees, then it would sign off on the red. So we continue to retard down to 5 degrees. And then the engine now bridges that gap over here to this curve. And then there's some really cool stuff going on here that I won't go into in this video. It's actually really important on how motocross bikes run, but a lot of road race and karting engines do not do that. So it's very important for motocross, but not utilized on the dyno graph, and we won't get into that in this video. So that's what a programmable CDI can do. It can bridge the three power curves that you would get by running three different straight ignition curves. But why? Why does a bike run like this? What is going on that makes this power curve shift? If it's purely about timing, surely there should be one timing value that would make the bike run most efficiently. And that's kind of how the four-stroke world works. Not exactly, but in the Chevy and road race and NASCAR world, they all kind of run really close in the ignition curve, maybe 30 or 28 or 26, but they don't stray much from that. So why is a two-stroke different? What is unique about a two-stroke that makes us have huge changes in our ignition curve? And with RPM, we retard the curve. What is going on with that? If you really have studied ignition curves on the four-stroke side, that wouldn't make sense to you. So let's talk about it. When you have more ignition advance, we have a colder pipe. Overall, the average gas temperature in that exhaust system decreases its temperature. Why? Well, we have more expansion ratio. The spark occurs earlier, we get more compression effect, and then the gas gets ignited a little bit earlier, and it burns more quickly, and it expands more, and as a byproduct of that, there's less heat remaining within that charge by the time the exhaust port opens. And as a byproduct of that, it goes out the exhaust at a lower overall temperature. Because of that, the pipe now works better at lower RPMs because pipes are speed of sound dependent on when the waves go forward and back. The hotter the pipe temperature internally is, the gas temperature, the faster those waves occur. Speed of sound increases with temperature. So that means that the waves will move quicker and work, I should say, at a slower, colder pipe. At cooler temps, the waves move slower. They take longer to get there and longer to come back. So if we build a pipe that's optimized right here, okay, then it's going to want a certain ignition value, which happens to be right here at 20 degrees, right? And it's going to want that because it's a combination of the best combustion, the right pipe temperature for the length of the pipe designed by the engine designer, and the port heights and other variables in our two-stroke. Everything's interrelated. They're all connected to one another to develop a package. So if we go with less ignition advance, we get a hotter pipe temperature because the gas hasn't started burning as early. It's still continuing to burn later on in the stroke, and sometimes, depending on how far we retard, which is why these curves go down so low, we're actually burning very late for optimized combustion pressure. We're way off of optimized combustion conditions, but we're trying to influence that pipe to extend our over-rev. So we're making that pipe extra, extra hot so that the pipe works really well to make horsepower. And a lot of people don't know, but on a two-stroke engine of today, all this horsepower comes from the pipe. If you take the pipe off the bike, I don't care what ignition you run, I don't care what porting you run, you're not going to make a lot of horsepower. And that's because the pipe is what moves all that air in and through that engine. The pipe is like a turbocharger or supercharger. It actually allows two strokes to move 1.5 times the amount of air that they displace through the engine. It's like having 1.5 times the displacement. And then it sucks a lot of charge through, and then that reverse cone at the back of your pipe is stuffing that charge back in. So making that pipe happy is what makes horsepower. So more ignition advance, more low end focus on the pipe, colder pipe. Less ignition advance, hotter pipe, more top end focus. And then at peak performance, when we design all of these variables together in that engine, which means that the pipe length, the porting height, the compression ratio, and everything is optimized at peak horsepower RPM, that's where everything's at its happiest. And we usually end up around on a production dirt bike, 6 to 8 degrees of ignition advance, but on race bikes, very commonly you end up at 12-ish degrees of ignition advance at peak torque. That's not peak horsepower, at peak torque. Typically that's about right. It can vary, but if you've designed everything about right, it's been found through combustion pressure analysis, optimum timing of when you should spark with a two-stroke head, which is much more efficient than a four-stroke head. We have a squish band and a nice compact combustion chamber that we can get optimum ignition around 12 degrees. It's about right. So that is determined by the engine builder. And then from there, we develop a curve that fills in the holes of our engine if we didn't have a digital ignition. That's what's going on there. Now let's talk a little further about what these can do. These are actually on a lot of modern two-strokes and going back a long time, also controlling a power jet. Well, what is a power jet, an electronically controlled power jet, as found on YZ125s, YZ250s currently, and formerly Suzuki 125s and Kawasaki and RM250s? Well, a power jet is a very cool concept that some smart engineers came up with. And so let's talk about what jetting can do. Just like ignition, when you change your jetting, a hotter pipe would be leaner, and a richer setting will be a cooler pipe. So if we had just one jet we could select, that's what would happen if we go a little leaner than perfect or a little bit richer than perfect. Perfect would be the best average power curve. So that would be something like, if I were to draw that power curve out, if we had quote unquote non-adjustable power jets and we had a perfect optimized ignition curve, we would see something like this. Would be a little bit better than that, and it'd be a little bit worse than that. So it'd be right in between. That would be one perfect jetting. It'd be the most horsepower we can get. It's going to be a little worse on the front side than a colder or richer jetting. It's going to be a little worse in over rev than a leaner jetting. So what does a power jet do, and how do these control that? What do we as engine developers and builders do to control that? Well, what we do is we have an extra jet in the carburetor that supplies about 20 to 30% additional fuel than what the main jet and all the other jets combined deliver. And then it can be turned on or off via a solenoid. And that solenoid can be controlled on or off multiple times. It's actually a pulse width modulated solenoid. So you can actually vary between 0 and 20% fuel that it can deliver, how much fuel it delivers. So what we do with the power jet is we open up that jet and allow the fuel to come into the engine at lower to mid-range RPMs to richen and cool the pipe more. And we get this beautiful front side curve. And then we modulate that power jet near peak power to get perfect fueling at peak. So we engage some of the control to turn off some of that fuel flow. And then past peak power, we shut off the power jet to excessively lean out the engine and heat up the pipe. And then we get this red curve. And then what happens is you get a power curve that is the best of all three, just like the ignition. We get the best front, we get the best peak, and then we get the best over rev. So by combining a power jet with an digitally adjustable ignition curve, we can now bolster up our overall power curve and get the best result possible. Additionally, we can design pipes and parts and pieces that help us make more horsepower than we could otherwise make without those features, because we would lose too much bottom end. If we didn't have all these features available to us, the engines would have to have a little less exhaust port and a couple other features, and the pipe designed at a lower RPM so that we could get a better average horsepower curve without all these advanced features. It's amazing how complicated two-strokes really are compared to a four-stroke when it comes to how they work and how they make horsepower. The pipe is everything. And it's actually why fuel injection on two-strokes is an extreme challenge, and what's plaguing current owners of fuel-injected two-strokes is that the pipe temperature is dynamic. It's never set at one number. And because of that, it's very hard to know how much fuel to supply at any given cycle, because for every single variation in pipe temperature, it changes how much air moves through the engine. And it's very hard to measure quickly and then deliver the correct amount of air in that cycle for how much is needed, whereas a carburetor senses airflow and delivers on demand. So we're going to get into that in another video. But this is what CDI curves can do. This is their basic function in theory. If you're new to two-stroke building and really want to get into it, this is hyper important. Understanding these factors and variables is how you learn to develop horsepower. So let's talk about why we use CDI boxes here at the shop. I sell mostly Gits for the majority of bikes that we work on. I also sell this HPI brand for bikes that Git doesn't offer CDIs for some of the older year model bikes that Git is not currently producing CDIs for. So what happens here? You can move your stator forwards and backwards and do this. You can move the curve up or down, but you can't shift the curve. So let's say I make an exhaust port change, and that's all I've done. I haven't changed the compression, I haven't changed the pipe, and I've changed the exhaust port. Porting is really well figured out by the manufacturers. They're smart. It's not like they don't know stuff that we know, right? So if I change the port and all of a sudden I get worse horsepower. So for example, I raise the exhaust port a little bit and the stock power curve was in green, and I raise the exhaust port, now it's in red. So I picked up some over rev, but I lost front side, right? Well, maybe possibly that motor did want that exhaust port change, but because it was no longer optimized on the ignition curve and no longer optimized with the pipe and the head, it doesn't really show up on the dyno yet. Well, how do we figure this out? So first off, you could advance the timing a little bit, potentially in this case, and say, oh wow, I picked up some power in the front, but I kind of lost some over rev, or hey, that's better, or hey, that's good, but it's not great. What's going on here? Well, maybe what needs to happen is maybe I need to change this curve, something like this, and it could be the same here. I'm just drawing it for you guys to see it. And so let's say it's the same, but then right here, I might need to do this. and then go over. And I might need this a little higher and then the same curve. Or I might need to postpone it and go a little further and then do this so that everything's advanced. And then go down further like this and go like that. Let's say I change the head, the pipe, the port, and I change everything. What happens now? Well, maybe that combination doesn't like this curve at all. And maybe it wants a completely different curve down here like this. Or maybe it wants a curve that goes out there like this, right? That's what programmable CDIs can do for you, is that we can change this curve. And by changing this curve, we can get the bike most optimized to make the best overall horsepower curve. That's what CDI boxes do. That's why we as a shop run them. If I were to sell you just our national level port job and head and pipe recommendation on, say, a KTM 125 or a KTM 85, it will run worse than a stock bike unless you package it together with our CDI. Why is that? Well, the stock CDI curve is not designed for our port arrangement and our pipe and our head arrangement and our carburetor and our jetting arrangement. Because of that, you can't make horsepower unless you couple it with a CDI box. And by doing so, we can make more horsepower than I can make by trying to port around the stock CDI curve, which for many years, a lot of builders have tried to do. With an adjustable stator, a lot of times the stock CDI curve will work. But in many cases, you might need to change that curve around. And that's why we sell packages and combos. We sell a combination that allows us to make what we feel like is more horsepower than our competition. And that's because we're putting a complete package together that influences all of these variables we talked about. And that is the route to success. And this is what factory teams have done for years. They've optimized the entire race package, not just one part of it. Now, our stock CDI curve's pretty good. Yep, they're smart. Those guys are really smart. Our stock port's pretty good. Yep, those guys are smart. It's not like you can just make a port bigger these days. Oh, and it's going to be better. Those guys know that too. So it's really about finding a lot of needles in a haystack and combining those needles together to build a complete package to make horsepower. It's not about one change or a head that's special or a carb that's special or one CDI. It doesn't work that way. It's all of those items combined together to make horsepower. Thank you for watching. I'm Derek Harris. If you have any questions about this kind of stuff, shoot me an email, leave a comment below, tell me how stupid I am or how smart I sound, one of the two. Either way, thank you for watching. I'll see you next time.